All right, our next speaker is Đorđe from Singapore Management University. They are presenting their work on verifying algorithms for differential privacy.
Hello. Excellent. All right. Hi, everyone. Thanks for coming to my talk. So my name is Đorđe Žikelić, and this is joint work with Krishnendu, Chatterjee, and Ehsan Goharshady from IST Austria. So today I will talk about our method SuperDP for refuting differential privacy by using Supermartingales. So let's set up the stage for the problem. So we are considering differential privacy, which is essentially a formal notion for ensuring privacy of data when basically extracting statistical data from, let's say, some database or set of information. So formally, given a privacy mechanism modeled as a probabilistic program, and given a notion of similarity of its inputs, we say that this mechanism is epsilon differentially private if for any pair of similar inputs, basically the total variance distance between the outputs, the output distributions of this program on these two inputs is bounded by e to the epsilon. So in other words, for any output event, the difference in the two probabilities differs by at most a factor e to the epsilon. And then we say that this mechanism is epsilon differentially private. Now the problem of checking epsilon differential privacy in general Turing complete probabilistic programs is undecidable. So of course we cannot have a single algorithm which can both verify and refute this problem. So people have focused both on DP verification on one hand and DP refutation on the other hand. And this is a very challenging and important problem because differential privacy is known to be, let's say, not very robust. So even minor tweaks to DP mechanisms can break DP guarantees. Now, recent years have seen a number of approaches and basically insignificant advances on this problem. And here I provide a summary. So I'm considering four, let's say, desirable properties. So one, of course, is full automation. Second is applicability to discrete and continuous distributions. The third is soundness. So basically guarantee that whenever a tool reports a DP bug, there is indeed a DP bug. And then finally, the fourth is semi-completeness. So what do I mean by this? So due to the undecidability of the problem, of course, we cannot have both sound and complete algorithm. But we could still ask for a sound algorithm which is guaranteed to catch a certain subclass of DP bugs. So some of the existing methods have focused on finite and discrete probabilistic programs. However, many differential private mechanisms use continuous distributions such as Laplacians or Gaussians. There is also a class of methods which use sampling and in some cases provide statistical guarantees. And these methods are automated and they support general distributions. However, they do not provide soundness guarantees. In some cases, they provide statistical guarantees, but as we observe in our experiments, sometimes it can also happen that they still provide false negatives, so report bugs in case when there are no bugs. CheckDP and its predecessors is a state-of-the-art static analysis tool, which is automated, provides soundness guarantees, is applicable to, well, they focus on Laplace distribution, but basically supports that continuous distribution. However, no existing method provides semi-completeness guarantees. And the question that we ask in this work is, can we have all four? So automation, applicability to general distributions, soundness, and also a certain level of semi-completeness guarantees. And we propose this in our method called SuperDP. Now, the key idea behind our method is we take a slightly different view on differential privacy refutation. So a standard approach to detect the DP bugs is to search for a pair of similar inputs and an event on output such that we have this probability mismatch. Instead, what we search for is a pair of similar inputs and a non-negative function over the outputs for which we have expectation mismatch. So expectation of the function on the output on the first input is greater than e to the epsilon times the expectation on the output given the second input. Now, expectation mismatch strictly subsumes this because for any output event A, you can take its indicator function, and that's your function f. But now, what does guarantee that this is sound? So this might seem we are considering a strictly larger class of objects. Well, we still show that this is a necessary and sufficient condition for detecting DP bugs. So in other words, a program is not epsilon differentially private if and only if there exists a non-negative function over outputs for which we have expectation mismatch. So now we may perform a search over this larger set of objects in order to detect DP bugs. And why is this useful? Well, for some classes of techniques, actually computing precise bounds on the probability of some events is quite challenging. Whereas there are also many tools for reasoning about bounds on the expectation of functions on outputs, which provide better quality bounds. And one such example of techniques is supermartingales, and in this work, at least to the best of my knowledge, we bring supermartingale certificates to the first time to the setting of reasoning about differential privacy. But before going into the details of our method, let me just give you an example of this expectation mismatch idea. So this is what is called the randomized response mechanism, which basically, if I have, let's say, some survey where participants provide yes or no answers, and now I want to query my database, I want to basically preserve the privacy of individuals. So what I do, if you query me about the response of a certain participant, with probability half, I will tell you their true response. And then with remaining probability, so 0.25 each, I will just tell you 0 or 1. So in other words, with probability 0.75, I'm telling you a true response of the user. And with probability 0.25, I'm telling you the opposite. So in that way, I'm trying to hide the response. Now, how can it is known that this mechanism is natural logarithm of 3 differentially private and is not differentially private for smaller values of epsilon. So how can we refute smaller values of epsilon? Well, we can use function over the outputs f, which is just equal to this output. So here I write output squared because this is what our tool computed, but because it's a Boolean 0, 1, this is just output. So the expected value of this function on input 1 is equal to 0.75. The expected value of this function on input 0 is equal to 0.25. So if I write my expectation mismatch inequality, I have 0.75 greater than e to epsilon times 0.25. And this holds exactly when epsilon is less than, so this is valid exactly when epsilon is less than natural logarithm of 3. So I can witness tight bounds using expectation mismatch. Now, of course, this doesn't solve the problem. I've just given you basically a new characterization of epsilon differential privacy. But the question is, how do I automate the search for this function? And of course, how do I automate basically reasoning about these expectation bounds? And for this, we are going to use supermartingale certificates, which have been already applied in probabilistic program verification and stochastic dynamical system verification to reason about various properties, including expectation bounds. So we're going to use something called upper and lower expectation supermartingales, which we used in previous works to also reason about equivalence of probabilistic programs. So these are proof rules for deriving upper and lower bounds on the expected value of a function on output, so which is exactly what we need to reason about expectation mismatch. So for upper bounds, what is an upper expectation supermartingale? So it's a function which to every system state assigns some real value, which is required to be equal to 0 upon termination. And then in non-terminal states, at every step, basically, the change in the expected value of this function over-approximates the change in the value of f. So basically, if I consider how f evolves over a program, basically, I over-approximate its change at every time step by using u. And this allows me to basically guarantee that, okay, this is a slightly simplified version. Basically, we have under conditions which are called optional stopping theorem conditions, which I'm not going to go into the details now, basically that U provides an upper bound on the expected value of F on output, and dually lower expectation submartingales for lower bounds. So we are going to use this as a tool to basically witness our expectation mismatch, because we cannot, in many cases, exactly compute the expected value of F on output, but we can bound it quite tightly by using these tools. So we propose a new supermartingale-based proof rule for refuting differential privacy. So we're going to search for 5 objects, 2 inputs, which are similar, non-negative function over the outputs, and then a pair of these upper and lower expectation supermartingales, which essentially allow us to witness this expectation mismatch. So the first, we have basically the first condition that we want these objects to satisfy. The 2 inputs should be similar. F should be non-negative function over the outputs. Now, L should provide me a lower bound on the expected value of F on the first input. U should provide me an upper bound on the expected value of F on the second input, such that this expectation mismatch condition holds. And this is essentially obtained by plugging in the guarantees of upper and lower expectation supermartingales on the expected value of F on output. And what we show is that, so this is sound, this follows from the soundness of upper and lower expectation supermartingales, but we also show that this is a complete proof rule. So for this particular application, we even get completeness guarantees. So this is a sound and complete proof rule for refuting epsilon differential privacy. And this is the important ingredient for soundness and semi-completeness guarantees. Now, okay, this still doesn't solve the problem of how do we compute them, but now we know what we need to compute. So if we want to refute epsilon differential privacy, we need to compute this tuple up there such that these 5 conditions are satisfied. And we use this by using template-based synthesis approach, which was also mentioned in the previous talk. So this is a general class of techniques for computing certificate functions. So basically you fix a symbolic template of a certain form. You collect the system of constraints over template variables which encode the conditions that you need to be satisfied, and then you solve. So in our case, we consider polynomial templates. So basically we assume that the program and the similarity relation can be specified in polynomial real arithmetic. And we basically fix symbolic templates, so for the 2 inputs, for the non-negative function outputs, which is going to be 1 polynomial expression, and for the 2 expectation supermartingales, so for each location in a program, 1 polynomial expression. And then we collect a system of constraints, which together encode these 5 properties. Now, I'm not going to go into the details, but essentially this gives you a system of quantified polynomial constraints over real variables. We have quantifier alternation, so that's not very nice to efficiently solve these. So we use a technique called Handelman's theorem, which allows us to, in this case, get rid of quantifier alternation, reducing the system to a purely existentially quantified system of polynomial constraints, which we can feed to an off-the-shelf SMT solver and solve more efficiently. And any solution to the system gives us a valid instance of this supermartingale witness for refuting epsilon dp. So we show that the algorithm is sound. It is also conditionally semi-complete. So what do I mean by conditional semi-completeness? So we showed here that this witness is sound and complete proof rule. But now we are restricting ourselves to polynomial real arithmetic. So our guarantees are, if this witness can be represented in polynomial real arithmetic, and if we use the needed polynomial degree, then our algorithm is guaranteed to find such a witness. So this is the semi-completeness guarantee that we provide. And then finally, the runtime of the algorithm is p-space, parameterized by the polynomial degree that you're using. We implemented a prototype, which we call SuperDP, hence the name of our paper. And we ask 3 questions. So first, how effective is our method compared to the existing methods in terms of examples that it can or cannot prove? How efficient it is in terms of runtime? And of course, what are the limitations of the method? So to answer these questions, we collect 15 benchmarks from the DP verification and refutation literature. Now, for not all of them do we know exact, privacy budgets epsilon that gives us type bounds. So we basically start from some low value of epsilon, and then we gradually increase it up to 15. And then for each tool, we report the lowest value of epsilon for which, its DP was refuted. We consider 2 baselines. CheckDP, which is a state-of-the-art static analysis tool for this problem, and then StatDP, which is a sampling-based dynamic method. And then for each benchmark, we set a timeout of 5 minutes. So this is the table of our results. I'll give you a summary of results as well. So basically, the green cells are, so in the first column, basically, the tightest refuted bound, the second runtime. So as we can see, SuperDP performs decently. Now let me give you a more qualitative overview of results. So for 13 out of 15 benchmarks, we successfully refute epsilon dp with the lowest value of epsilon compared to all the tools. Now I will explain what happens with the last 2 examples when I talk about limitations. In all cases but one, our runtime is less than 3 seconds, so we're quite efficient. For examples where epsilon less than 15 is sufficient, in 7 out of 9 examples we find lowest bounds. And then in 6, where epsilon needed is actually greater than 50, we refute 15. I don't know how I'm doing with time. Do I have... Okay, then I can go a bit into the insights, some more detailed insights. So this is some examples of benchmarks where we observe different things. So for instance, this low prob benchmark is an example of where in order to refute the DP, you need to reason about low probability events. So this is typically a class of example where sampling-based methods will struggle because you need many, many samples to detect these. SuperDP manages to refute epsilon differential privacy in this example. We are also able to handle examples with unbounded loops, which is also very challenging, such as geometric. And then we are able to handle a broad class of different probability distributions. So basically, the only thing that we require is that we have access to the first D moments, where the D is a polynomial degree that we're using in our algorithm. So this is good side. Now, what about the limitations? So I mentioned that we fail on 2 examples. And actually, the reason behind the failure is the same. So there is a construct which is common to these two examples. So basically, we have a sampling instruction from a Laplace distribution, and then we have conditional branching based on the result of the sampling. So in order to perform static analysis on this, you need to kind of symbolically reason about the probabilities of these bounds, which if you're using general probability distributions and then you condition based on the result, is challenging to capture accurately using polynomial arithmetic. So this is one limitation of our approach. So such constructs, we need to go beyond polynomial arithmetic. More generally, we are restricted to programs which can be represented in polynomial real arithmetic. So the similarity relationship between the inputs and all arithmetic expressions need to be polynomial. Now, this doesn't mean that our distributions need to have polynomial PDFs. They can have non-polynomial PDFs. So Laplacians and Gaussians are completely fine. We just need to have access to their first d moments. But the arithmetic expressions appearing in the program, they need to be polynomial. And then finally, we consider epsilon differential privacy, but there are also more general notions of differential privacy, such as epsilon delta. So this is a subject of ongoing work. We have some interesting results, and I hope that I'll be able to present them soon. So of course, addressing these real limitations is, naturally interesting directions for future work. And of course, another one is going to DP verification and trying to obtain sound and semi-complete algorithms there as well. Oh, wait. Oh. Thank you, but I have one more slide. So to conclude, basically, maybe the key takeaway from our work is that we reformulate epsilon differential privacy as an expectation mismatch problem. So this is kind of a different view on epsilon differential privacy. And then one way to tackle it is to use Supermartingale certificates. So this is something that I've been working on for years, and I'm very happy that we're bringing them to a new application domain. So basically, one can design a sound and complete proof rule for refuting epsilon DP by using Supermartingale certificates for expectation bounds. Based on this proof rule, we design a sound, semi-complete, and fully automated algorithm for based on template-based synthesis for refuting epsilon DP. And our prototype implementation shows promising results. So we are able to solve 13 out of 15 benchmarks at good runtimes. And our tool is available, so you're welcome to play with it. And I haven't written it on my slide, but I'm also having openings for PhD students and interns. So if this sounds interesting, please come and talk to me. Thank you very much.
Thank you, Đorđe. Any question from the audience? Yep, I'll give you the speaker. Yeah.
Hello, I'm Shaurya from UIUC. Very nice work. You mentioned to have used Handelman theorem while using. If my understanding of Handelman theorem is correct, it is only necessary if your space is bounded, like on a polytope. But if you are using continuous distributions, then the variables can be unbounded, right? Mm-hmm. So how does that work in that case?
Right, that's a great question. So soundness is not affected. So basically, this translation provides semi-completeness guarantees if the space is bounded. So you can use sampling from continuous distributions, but the support needs to be bounded.
Oh, so the semi-completeness comes from the fact?
Yes. Needs to be. Well, you can have semi-completeness even without this. So this is done for efficiency.
Makes sense.
But if you want to have p-space runtime, then you need to apply this. Yeah.
Fair enough. Thank you.
Other questions? Yes, in the back.
Thank you for the very nice talk. I was just curious, like, what degree of polynomials do you consider in your experimental results? Like
up to 5.
Okay, thanks.
All right, we have time for one more question. Yeah, Philip?
Thank you. Yeah, lovely talk. So you already mentioned that you're interested in extending this to epsilon delta. How about other notions of differential privacy? There's many more.
That will be interesting. We haven't considered that, but yeah.
Okay.
So as the first next step, we started with epsilon delta.
Right. Yeah. Because those testing-based characterizations might start breaking down.
Yeah.
Interesting. Thanks.
All right. Let's thank our speaker again.
Thank you.